Hello everyone. Today I'm going to design an analysis of residential building of three-story. Okay, first I'm going to open the e-tabs and I'm going to select the new model. Okay, now we are going to use BS building setting with our unit will be in SI unit. Okay, then design different. It will be in India. Okay, and still selection will be like I'll take from right now it will be India and steel design code will be as S8000 and concrete design will be as 456 2000. Okay, uh, this is our design code for design code. This is our design code for concrete and steel. Okay, will okay, I'll click OK. Then we need our uniform grid. Okay, uh, let's see. We have for for horizontal we have 1, 2, 3, 4, 5, 6, and for vertical 1, 2, 3. Okay, three just and we have to have different spacing. Okay, we have like different spacing. Number of grid in X direction. Mm, I'll just keep it there and I'll change it later on. Okay, just click here. Okay, okay, okay. Next, I'll open this one. Then I'll open my grid. It is student grid. Then I will modify and show grid. Okay, and we have like different grid here. And let's see the AutoCAD. We have to drawing here like in we have the unit in feet, but we need in meters. So right, I'll click here right D, click enter and modify it. And I'll go to alternate unit and display alternate unit. Okay, it will display in uh, close. We close it. It will show in meter. Okay, okay. Uh, let's start with X direction. Okay, I will start from X direction. It's like 3.352. Okay, let's go here and I'll go display grid on spacing this A to B, and we have A to B here 3.352. 3.352. Okay, then we have B to C is 3.352. Okay, then we have 3.352. That's it. We do not have we do this 0 and we do not have D. Okay, 1, 2, 3, 4. Now we're going to space here. Okay, let's see. It will be you can see in the figure what is our 1, 2, 1, 2, 3.0 and 3.103 013. Next we have 4.013, 4.013, and next we have 1.524, 1.524, and next we have this here another portion is here. We'll keep later on like 3.759, 3.759, 3.759. and our last will be 3.759, last will be 5. Okay, it will be, let's click OK. Then we'll go to modify storage data, and we'll keep the this story base. Right now we make uh let's assume story will 3 meter. Okay, now it's fine. I'll just keep it 3 meter. Okay, then I'll click OK, and this is our grid. Okay, next we will define the material. We'll go to define, then we'll go to material properties, and here we have the material, but we'll define another we'll add a new material. Okay, we'll go to add India region. Material type, we'll define the concrete, and standard will be India, and concrete frame will be uh, based on just okay. So if we click on the material, okay, if we start the material, it's in place. I'll go here, and in the grade of concrete, it's like if EVM 20 for more than 12 meters height, and shall be EM 20, and still be rate will be still shall be of rate FE 415 or less. High strength deformed steel bar produced by elongation capacity more than 15%. Okay, here it is given. We have given the grade of concrete and the material, which material to use in our country. Okay, okay, let's go. I'll define the. I'll assume the M25. Okay, our building height is more than 12, and I'll assume I'll assume this M25. Okay, and we have M20. Okay, it's 20 minimum grade. Okay, I'll add it. Okay, and looking the concrete is we'll keep the same concrete to concrete, and this is the metal properties is defined by the it type itself. If we do not need to change anything, we'll click OK. Then we'll add another material, which then we need to add steel rebar, and we'll add our rebar. Then it's in especially we can use anything like Western code. I'm going to use like 500, and it's HSD, and this of properties. You can write FE 500, and we do not need to change anything, like it's all same. Okay, and we'll click OK, and then after we have add our concrete and bar section. Next one is we'll define our section. We are going to section, we are going to section our frame, and we have different frame. I'll delete this all one. We don't need anything like this. And sorry, we will delete everything. You don't need this one. Became very slow. Okay, we need a fast processing laptop for it. Okay, then we'll define our column and beam. First, I'll define the new material. Like I'm going to need a frame structure, so I'm using the concrete, and I'm going to the I'll damage column of 300 into 300. For our structure, the minimum size of column is 300 into 300 as per NPC 105 to 105 code. And material, we are going to use M25, and complete rectangle we are going to use 300, and width is 300, and we want to we modify the reinforcement. We can see here we are going to divide column, so it's there. We are going to longitudinal bar of the 500 and component bar of 500. and we are going to use clear cover of 1.40 mm and number of longitudinal bar 3 and 5. Total we need 8 bars in our column as per our code, and longitudinal bar size, and we can use at the corner longitudinal bar we can use 12, and corner bar we can use 16. Compounded bar size area we can use 8 1 for tie, and longitudinal that's so it's only the guess we have given for the design. Okay, let's click OK. Uh, uh, Next, we need to modify our properties. Okay, why we should do this one, I'll tell you in the video. Okay, let's go to the code. Um, uh, on the it's the this one is the effective stiffness of cross section. Okay, what is the reason is we have like this in our new NBC 2020. It has given about wall over shear wall, uh, but we have these beams and column in Indian standard called earthquake code. Um, and in our NBC, it has given, it has add something like wall section. And okay, the reason is when it is in a regular analysis, we use the like stiffness and modifier 1 1, uh, because the gross movement inertia is taken as 1, but it's 1, and it will take fully load everything. But when the structure is loaded, like when there is earthquake, that structure element get cracked. Like that's the reason. When the crack gets, the structure element get cracked, and the crack will occur when the crack is mainly occur when there is uh, tensile tension in the frame, and uh, so the crack will like it will come in the flexure region, and the crack region do not have the gross will not take the whole gross moment of inertia. So we need to consider the uh, effective. We need to consider the mode, like we need to consider the stiffness modifier for this analysis. Okay. Uh, Wha- After the crack, the like that the building became more flexible. But when we do the analysis, we consider that the building is fully stiff, but it does not happen. For real practice, we use the modify. Uh, to have our real practice, we use the modification property modification of the beam. Like we assume that the building is stiff, but the building became flexible. So there will be more drift, and to get the real result, we use the mod modified properties modifier. Okay, okay. We can see that we have the beams, we have uh, beams and column. Like this is our code. Okay, in NBC 105 2020 effective stiffness of cross section. Our structural analysis shall be performed in arriving at the elastic flexure and shear stiffness properties of cracked concrete and masonry element. In absence of such analysis, the effective stiffness of cross section shall be taken from the table. Here we have the beam, column, wall, cracked, uncracked, and we have the flexure stiffness and shear stiffness. Okay, okay. You can see that the beam and the column have different flexible stiffness. What's the reason for this? I will tell you. Like beam is the flexible element, and the column is the axial element. Like column is subjected to higher axial force, uh, whereas the beam is the flexible element. Yes, the extent of cracking on column is less than the beam, because in beam formation of cracks are more because of flexible elements. So they have the higher chance of having the cracks, and the moment of inertia is less of beam than column. Yes, we can see this. We can see that it has a different value, and let's see where the these values affect our analysis. Like As you know, in strength of material, we used to have like movement distribution method where we use one and one, and and we have like movement in this like movement distribution method. We used to use like we use the same moment of inertia, but but in in the intersection, like it mainly affects in the intersection like beam to column. The intersection of these two elements are critical. Like we have the different momentum in its share. We can see it like beam have the lesser moment of like flexible stiffness, and column has the more. Yes, so it affect in the intersection of these elements, and this element like this element the intersection, it became the more critical and attracts more movement, and which induce higher stress in this region. So we can have like in the intersection region we'll have the more movement, more reinforcement, and more detailing. So more detailing. So we are going to use the effective stiffness for our analysis. Okay, let's go to ETABS, and I'll show you where we can use that. Okay, this one is from, we have the cross, we have the shear one. Let's see our code. Okay, for shear one 0.4, 0.4, and flexible 0.7. Okay, 0.4. Okay, in two direction 0.4, and we can use 0.7 and 0.7. Okay, by this way we change our properties modifier. Okay, next one. Okay, next one will be, I will add a beam. Now next I will add the copy properties. I drag the beam. I'll make 230 into 350. Okay, naturally 25. Okay, to be fine. Concrete depth will be 250, and width will be 230. Okay, I will assume it, and then we're going to modify shear reinforcement and beam William street design. FE 500 minimum top bar, minimum cover will be held at 20 minimum cover as per our code. Okay, then it will be okay. Then we'll show our uh, modifier, stiffness modifier. As we can see in the code, beam we have 0.35, shear 4, shear by 0.35 for flexible stiffness. Okay, it's 0.35, 0.35, 0.4. Okay, can click, we got it. Then you can click OK. Next will be like define section properties. Now we're going to define the slab section. Okay, I'll modify this modify properties. I have slab 125. Okay, slab type, material type, it will be M25. Middle seal thin, it will be seal thin, and its size will be 125 Okay, and we have defined our all material properties. Okay, uh, I forgot to define one more things like section. I need to define this one with full cell, and I need for staircase also. Okay, I'll click for staircase. Okay, staircase, stair 150 25. Okay, 1 pm. This is for staircase, slab here, stair, everything we have got. Okay, now we have defined our all section. Now we are going to define a load pattern. Okay, for that load we have 1, and for live block 0. Now I'll add another load. Okay, next one will be the wall load. We'll consider wall load. It will be dead, and it will should multiply will be 0. Then we have partition load. Partition load. It is dead. We'll add new load. Then partition, and then we have floor finish. Floor finish. stated date. Okay. After performance, we have steer date, steer date load, this date, and we have steer live load. Okay, that will be the live load. Then next will be the water tank load that will be live. Next one where we need to define the earthquake load. Yes, okay. In previously we used to define the earthquake like EQX and EQY. Um, that was for ultimate limit state, but now code NBC 105 it tell us to use now ultimate load limit state as well as service limit state, but we need to define the load in separately and analyze separately. Okay. Before defining the earthquake load pattern, we need to know about the horizon specific base here. It is the total earthquake load acting base of the structure, and here is the formula: B is equal to CDT1 W. This is the formula, and this one is horizontal base shear coefficient as per 6.1, and W mean is the specific weight of the structure at as per 5.2. Okay. If we go to the 6.1, we have like two limit state, like ultimate limit state for and we have the formula CDT1 CT1. Here we have given the CT1 elastic side spectra as per 4.11, and ductility factor as per 5.3, and overstate factor for here we have given every formula. And for serviceability limit state, elastic side spectrum determined from the for service state limit as state for 4.2. If you go to the 4.2, we have everything like here. Okay. 4.2. Okay. Yeah, we have given tuning factor. Everything is here. You need to know about it. Okay. Spectrum factor as per 4.2. 0.3, 4.2 look, 0.2 CT1, and elastic elastic side spectrum for horizontal loading determined from 4.11. For service library, it is usually taken as 20% of the elastic side spectrum from ultimate limit state. Okay, and for our mu ductility factor for serviceability is taken as 1. This is what we have the formula. And if you go to consider that every factor is given in here, and we need to go for every section. Like if let's go to the um, if you go to the 5.4.2 for self-stability limit state, we have like we know the structure system, and we know that our structure reinforcement movement resisting frame structure. So it's a reinforcement concrete movement resisting frame, and we have our new everything here for everything. If we need for another one for ultimately state, we have here. And as I told you, the ductility factor is is taken as 1, and it is everything which we need is here. Okay. Next, if we go to okay, 61.4 as per 4.1.1, elastic side spectrum, it is given for This is loading given by equation. We have the equation like CS2 CS31Z I1 seismic zone factor as per 4.14 and spectrum shape factor as per 4.1.2. Okay, let's go to spectrum shape factor, and it depends upon the type of soil which we have and through which and period we can get our CST time. And it is like we have two one like for equivalent site static method, and 4.2 it is used for movement response spectrum factor. Okay. And we see which one to use, which mode of statistical method we need to use. It is given on code. The top you can see that, yeah, analyze applicability of analysis method like for equivalent static method for ultimate load static ultimate limit state or equivalent static method may be used with at least one of the following criteria is satisfied, like the height of structure is less than 50 meters, the measure of time structure less than 0.5 second, and the structure is not categorized as irregular as per 5.5, and height is less than 40 meter. If it meet all the criteria, then we are going to use equivalent static method. Otherwise, we are going to use model response spectrum method. Okay. Okay. And then can we have all the things for equivalent static method, then we can calculate it, and it is given like here. Look, on the basis of TA, TC, A, or yes, by the formula also we can calculate the spectrum shape factor as factor, which is here, and based on the soil type, it is given like very steep. The properties of soil is given, and the difference is we have like cohesionless material or something else, and it is given like a period like 0 for type 1 cell it is 0 is less than 0.2 seconds, type B cell is 0.6, type C 0.6, and for type D is given 1 seconds. Okay, and it is for Kathmandu Lalitpur, Uttapur, any other region is given, and Z. Next one is seismic zoning factor, and it is given here. Everything values for uh, different cities given here. Okay, and important factor like the structure, the importance of structure based on the importance of the uh, function and category. Uh, it is categorized on different classes, and I'm going to use like 1.5 one. Okay. Okay, let's define the earthquake load. Okay, okay. Now we're going to add earthquake load on. Our load pattern for constructive, our load combination. Let's add it like QQ X QWS, and we'll write it. This is our seismic load and multiply 0 and auto lateral, and we'll use user coefficient. We'll define it. Add new one. Then we'll have two y-axis seismic. Then we'll use service limit state. Okay, service limit state y-axis, and then going to use service limit x-axis. Okay. By this way, we are going to define the load for our structure. Next, now let's go to calculate. We need to modify the load. Sorry, modify that lateral load. So it's on x direction. So we are going to untick it, and we need the base shear coefficient and building height exponential. Okay, for this I'll let you know how to do. Okay, first I have the Excel sheet. I'll save it. Okay, and we know that we are going to NVC 105 2020. We know the seismic zone factor. Let's go. It is in 4.1.4. I'll tell you by step. 1.4. Okay. it's the seismic zone factor. So for seismic zone factor, I'm going to use like anything like one value like Bratnag or something. Okay, Kathmandu, and then so, yeah. And then next I'm going to use for important factor, the importance of building. Okay, for just not falling class one, it's not school college cinema, so I'm going to assume it importance factor one. Then height of building we can know from our ETF, okay, ETF model. Okay, this is the, if you click here, you can, if you click here, you can get the height of building like 12 meter. Okay, okay, next go to the soil type. We're going to, okay, for soil type you need to go 4.1.5. Okay, 4.1.5. Oh, no, it's forgot it is here, sorry. We have here soil type. Based on this soil, we can assume it for our value. We are going to use type 3 soil type A. Okay, and okay, after that it's done. Okay, everything information we are assume, we have assumed it, and we know which type of soil it is based on the soil report like geometric geotechnical method like soil testing report. Okay, now we are going to calculate period of vibration. Okay, for input movement, and we know the out frame is movement resisting frame. And if you go to code 5.1.2, we have the empirical expression equation, like we can calculate the time period of frame. And if one is T1, then KT is 3/2. It is our movement resisting concrete frame, so 0.075. And we have the height of building, and we can calculate the approximate like fundamental of vibration like empirical. Okay, this is not exact. I'm talking, yeah, it's given here. Everything is given here. Now, now after that, we're going to the 1 2, and 1 2. We have this. We need to calculate the elastic side spectrum for horizontal loading. For this, we can calculate from this table, and based on the soil type. Sorry, it's D, I think. It's D. Okay, sorry. Where is it? Based on the soil type, we have the lower upper period of flat look is 0.5, but yeah, this is a equivalent static method as I have shown you previously, like its height is less than 15 meter and it's not irregular building. So T is 0, and upper period of flat period part of spectrum is TC is 2. And then we need to calculate peak spectrum acceleration normalized by PGA. It's given 2.25, and we have given K 0.8. Okay. After that, we need to calculate the spectrum shape factor like CST. We are going to calculate it, and CST is equals to, we need to look at the condition which is satisfied, and we have the T1 time period of 0.6044, which lies between TA and TC. Okay, that means it satisfies the this condition, and we get our CST spectrum shape factor 2.25. Okay, and after that we need to we have this formula, and we are going to calculate elastic size spectrum for horizontal loading, and CSTZ we have spectrum shape factor, and we have the seismic zoning factor and importance factor, everything we have. And by the formula I kept in the Excel and get the value from here. Okay, and this is for, yeah, strip factor. Okay, this is for the horizontal loading. And for now, if we go to the down, open to, we can see for here we need elastic spectrum from solubility limit state, and its elastic side spectrum solubility is given by 0.2 times CT. and if we multiply that, we get the elastic side spectrum. Okay, everything we have. Now we are going to carry the horizontal base shear coefficient. Okay, we'll go to the down, go down, 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 and our structure is reinforcement concrete frame, movement resisting frame. Okay, uh, that means we can help RU means ductility factor, overstrain factor, and overstrain factor for ultimate limit state, service limit state. We can get here from this table. We get this value, and if you go to down, 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 we have here formula in 6.2, and we kept the value like for ultimate limit state. The original base year coefficient is CT1 RB in overstrain factor, and we get the value 0.13125, and for the serviceability we get 0.126. And next one is we need, and we are going to place this value in our ETABS. And another is we need the exponential related to structure period, like we need this value also in our in our ETABS. I'll show it where we need. If you go to 6.3 force, it is given here, and exponential related to structure period, and for structure having time period less than 0.5 it is 1, and greater than 2.5 is 2, but it lies between here. So by interpolation we get our value 1.065 because it lies between 1 and 2. Okay, I'll show you how we are going to use this one. Okay, load pattern. If we're going to the structure ultimate ultimate EQS ultimate, then I'll take this one, this one, this one, and from our Excel sheet we have ultimate. We have 0.1313125, and building exponential height that is fixed for every all the buildings. So it is 1.065, 0655, and this I'll copy this one. And you need the exponential ratio all draft. It's also given in the code. If you go to the code 5.7.6, all analysis for torsion effect. The applied torsion at each level shall be either the force calculated by equivalent string method or combined story initial force found in a model response spectrum method. The accidental eccentricity can be taken as 0.1. So we are going to take is 10% 1, and it's going to story for 2 days, and it's okay. And we're going to divide for similarly for this one modify. Do we have here? Oh, sorry, 1.05, it will give 10%, and we have 13131. Okay, then we're going to this one 5. Molecule go to lead. Then we have this one. We have 0.126 6. It is y-axis, and then it is control B is 10%. Okay, this I did on. Okay, I did it. Okay, and axis is 2126, and this one here, and, and x-axis. Okay, by this way we define our load for our uh, load pattern. Uh, uh, Now we're going to consider the load combination. Okay, go to the define, then load combination. I will add new combination. We have in the, let's go to code 3.6, load combination for parallel system and non-parallel system. We have like parallel system means if the columns are in the grid, it is called in the parallel system. And in all parallel means in the, if they are in not in the grid, like in the different position, like if the column is here and next column is here, then it is in different position, in different condition, and they have like some eccentricity. We need to consider some eccentricity for the design. Okay, for our building design, we have like in the same grid, and now we're going to use the parallel system. Okay, first load is combined, and we are going to use 1.2 dead load and 1.5 live load. Okay, first, okay, let's go here, and 1.2 dead load plus 1.5 live load. Okay, this dead load here is 1.2 dead load. Then we have wall load. Then we have partition load. Then we have floor finish load. Then we have stair rate 1.2 enter 1.2 enter floor finish entry enter 1.2, and we don't need this unit. Then after unit live load 1.5 add, then stair live 1.5, and for water tank uh, I think for water tank we are going to use 1.5. No, we are using 1.5 for water tank. Yes, water tank also, there's also live load, so add this 1.9. Okay, this is our load. Okay, we see, add copy of it to tank of, that's it. Let's see it. What is your combo? Water tank. Yeah, we have everything. Water tank. Yes. Okay. Now, next one is we need to consider for dead load plus mm, plus live load plus eccentricity. Okay. Okay. No, earthquake load. So, on the purpose of storage, we are going to use our live load for like it's our residential building. So we are going to use 0.3 for, okay, for other purpose. Okay, let's add it. Add copy combo. It is 1.5 live load and 0.3. Okay, okay. That is one live load, one partition load, one code finish, one there, one enter live 0.3, 0.3 water tank 0.3. Okay, what is this? Uh, tank water tank still live 0.3. Yeah, don't need this one. And then we're going to use eccentricity EQX. For our analysis, we are going to use like ultimate limit state. We do not need to use like surface limit state. The value of ultimate state limit will come grade 1. So we're going to use EQX add, and we don't need this one. This one delete. That's it. Okay, we got it. And add curve combo, and we're going to use minus -1 in the both direction. Okay, and then need to add copy of combo view. Then it will, we will consider y direction y direction. Okay, combo of copy and go to minus it will come -1 in y direction. And sorry, you don't need to delete this one. Okay. And we have like four combination if px. Okay, minus. Okay, here is our load combination as per our code. Now we're going to define the merge source. Okay, we'll modify and I'll modify this merge source. I will remove the limit spectrum. I will select specific load pattern. Let's okay, sorry, 1 minute and then we are going to add date load one. Load sorry, date load one load one. Then after person load one, for finish one, and step step date one. Okay, step live will add one. Right, I'll show you what a time. Okay, if you go to the code on code 5.2, 5.2, if you go, yeah, we are given like the specific library shall be determined by given in table 5.1. Like so, we are given storage 0.6 and for other ports 0.3 and roof nil. But I'm going to use for the roof. Um, for the roof, we are going to use 0.6. Let's consider. I'll consider that one for our analysis. Okay, this I'll use like for roof tank like 0. I'll use 0.3 before for state life. Anything you can use like this. Based on the purpose, you can use anything. And if you want to use life, you can use it. Yeah, by this way, on the basis of your needs, you can define your merge source. Okay, I've defined my merge source. Okay, uh, okay. Thanks for this one part one. Then I'll consider part two in next video. Thank you.